Hello students, in the previous two lectures we had studied scalar triple product of three vectors, its definition and properties. Now in this lecture we'll study some special problems of special triple product in Cartesian form. For that, the first article, that is, if A vector have three components A1, B1, C1, and B vector have three components A2, B2, C2, and C vector have three components A3, B3, C3, then we then prove that scalar triple product of ABC is equal to determinant of component of first vector in first row, component of second vector in second row, and third component of third vector in third row. Proof of this is, we have taken left hand side, that is equal to scalar triple product of ABC, which by definition will be equal to vector of A dot B cross C. Now, in order to solve this, we have to apply BODMAS. Therefore, we have to find B cross C. So, we have read in the earlier class that the cross product of two vectors is written in this determinant form. And determinant for the solution determinant, let me give you the generalized definition to find determinant by operating by any row or by any column. So I am giving you by operating the first row or first column. So if I consider a nth order matrix, then determinant of A will be given by, I am operating it by first column is equal to I is from 1 to n, summation I is from 1 to n minus 1 power I plus 1 AI1 MI1. MI1 is the minor of the element AI1. What is the minor of the minor of any element? Minor of any element is the determinant of some matrix obtained by deleting the row and column containing that element. Similarly, if we operate it by first row, then the value of determinant will be, value of determinant of this nth order square matrix will be j equals to 1 to n summation minus 1 power 1 plus j, a 1j and 1j. Now let me operate the determinant, this determinant by first row. The form, this formula will take the form for this third order matrix is j varies from 1 to 3 minus 1 power 1 plus j, a1j and 1j. When we will operate this summation, we got this result. We give the value j is equal to 1, j is equal to 2, and j is equal to 3. Now, when we apply this to the to substitute the value from this b cross c, we got a1 is equal to iota and minus 1 power 1 plus 1, and cofactor of this will be equal to this row and this column determined of this b2 c2 b3 c3. So this is minus a11 minus of iota plus minus 1 power 1 plus 2 j is the a12, so element of first row second column into m12 is the minor of this element. We delete this row and this column determined of a2 c2 a3 b3 plus minus 1 power 1 plus 3, and a13 is equal to rotator k, and minor of this will be a2 b2 a3 b3 determinants. When we solve it, we got this this expression. So now this is b cross c is equal to this much. Now substitute the value of this in the scalar triple product a vector dot b cross c, this new vector. So when we find the dot product of two vectors, we have read in the earlier class, dot product two vector is the product of their components. So multiply them. This vector with this. So we got the product of their components. This component plus this component to this component plus this component. C1 into this component. Now we'll write this in the matrix form, the reverse order. So we'll apply the definition of determinant. This is the first element, and this is the minus element. This into this minus this into this. We write the B1, C3, and minus B3, C2. This is minus 1 power 3. Minus sign is here. Now again, element A1, 2 is B1, and this is equal to minus this will be A2, A2, C3, A2, C3 minus A3, C2, and so on. So we have converted this in terms of a determinant form. The triple product, scale triple product of ABC is equal to compute of first vector in the first row, compute second in the second row, and compute of the determinant. Hence, now next article. If ABC are any three vectors in space, then prove that determinant of A dot A vector, B dot A dot B vector, A dot C vector, B dot A vector, B dot B vector, B dot C vector, C dot A vector, C dot B vector, C vector, determinant of this is equal to square of the scalar triple product of ABC. For to prove this in component form, let A vector has three component A1, B1, C1. B vector has component A2, B2, C2, and C vector component A3, B3, C3. C3. We can prove both ways, that is by left hand side right hand side or right hand side by equal to left hand side. One way will be proved by me and other will be proved by you. So I'm taking left hand side. Left hand side is determinant of this A dot A, A dot B, A dot C, and so on is equal to A dot A is equal to dot product vectors product of the components. So A1 square, B1 square, C1 square. Similarly, A dot B is equal to A1, B2, A1, A2, B1, B2, C1, C2. This is the second component, second element of this determinant. A1, 1, A1, 2, A1, 3 will be A1, A3, B1, B3, C1, C3, and so on. We'll use the dot product of directly in component form for all the 9 elements. Now we'll write, how will we get this matrix determinant? We'll convert it into two matrices first. First is this is row to column operation. First element is of this is matrix, first matrix A1, B1, C1, and the element of first column will the second of the second matrix will be A1, B1, C1. Similarly, A1, 2 from R1, C2. R1 is A1, B1, C1, and C2 will be A2, B2, C2, and similarly A1, 3 will be we'll get in the similar fashion. And by doing this for all the 9 elements, we have converted this determinant of this matrix into product of the product of the two matrices. Now we apply the property of determinant. Determinant of product of two matrices is equal to product of the determinant. So when this was product of two matrices, so we have converted that to product of two determinants. Again, we will apply the property determinant. Determinant of a matrix is trans to the matrix. So determinant this matrix is equal to trans to this. So we get both the matrices same. Therefore, this matrix and this matrix equal to this matrix square is equal to what is this? This is the determinant of the this is the scalar product of ABC, and square this, this is right hand side, and this is both. Now in the next article, prove that scalar product of ABC is equal to determinant of their components. First row, first vector, second row, second component, second vector, the third row, component, third vector, into scalar triple product of LMN vectors. where LMN three vectors are non-coplanar vectors, and AI, BI, CI, I use 1, 2, 3 are the components of A vector, B vector, and C vector in the direction of L vector, M vector, and N vector respectively. Now L vector, M vector, N vector, they are not the unit vectors, they are any three vectors, three known vectors in the three-dimensional space. So we are given, therefore vector A will can be written in the forms of, the components are A1, A1, B1, C1 of vector A in the direction of element. Therefore, vector is written in A1L plus B A2M plus A3N. Similarly, B1, B2, B3 are the components of vector B in the direction of element L, M, N vectors. Therefore, B vector is written in the form of B1L plus B2M plus B3N. And similarly, C vector can be written as C1L plus C2M. Now, you know what we have to prove. Scalar product of A, B, C is equal to this. So we have taken the left hand side of the left hand side. What you have left hand side, and prove that's in right hand side. So left hand side is equal to scalar product of A, B, C. By definition, this is equal to A dot B dot C. So if we want to, if L, M, N are unit vectors, then we can find the cross product in this form. But here L, M, N are not unit vectors, so we can't find by writing this and writing this B and C vector in this form, and we can't evaluate their value of the determinant. So we have to directly multiply them. This is very interesting and special thing here. If element is unit vector, then you can do it this way. If element are not unit vector, then you have to directly find their product. So when you multiply B and C vectors, so we will get 9 terms. We will get 9 terms, 3 from this, 3 from this, and cross product. So we know that the cross product of equal vector is equal to 0. Now substitute value L dot L is equal to 0, L cross L equal to M, M cross M, N cross N equal to 0. We are left with 9 terms. Now we'll write the terms in vector form in the cyclic order: L cross M, M cross N, N cross L. So we convert this term. This is L cross M, L cross M, L cross M, and at the time is M cross L. So if I convert this into L cross M, this minus sign will be here. So, and both the terms will be combined. L cross M will be common, and this will be B1 C2 minus B2 C1. B1 C2 minus C1. Similarly, we'll combine the terms of M cross N and N cross L. Now, this we got a B cross is a single vector. Now we'll substitute the value in scalar product of ABC. We'll find the A dot B cross C vector. So A vector dot B cross C vector. So when we find their product, we'll again get 9 terms here, 9 terms here, 3 from this, 3, 9 terms with this, and uh, and we'll apply two properties of scalar product. One is, if out of 3 vectors, 2 vectors are same, then the value scalar product is equal to 0. And second is, if L, M, and R change the cyclic order, then the value determinant will remain the same. By using these two properties of determinant, we will reach, we will be left with with this solution. With this solution, other terms will be cancelled or become 0 into L dot M cross N. Now this is the value. This is the value of scalar triple product of A in the first article, that this value become component of first vector, component of this first vector, first row, second row, and third component third way. In terms of this term will reduce, can be converted into this matrix form. This will be return form into element. Hence, the result is good. Now, in the next lecture, we'll solve problem based on scalar triple product, and we'll use the properties to find the volume of the parallelopiped found by the fixed vectors, etc. And the lecture will be on the Google Meet. Thank you very much.